a great pleasure for me to introduce my friend Stephen Theriault, whose work with Jelena had a very strong influence on us when we started getting interested in this subject. A very strong influence. I've always had a very high regard for their work, so it's a particular pleasure, Stephen. Thank you.
Thank you, Tony. So this will pick up where Martin left off, in a sense. So in desuspending the homotopy equivalence he was talking about. So I'll restate the theorem. So he talked about a general XA case, all right, but I won't talk about the XA case. I'll specialize a bit to Conon AA case, where, so this would be the case where the A is including trivially into the Conon A because the Conon A itself is contractible. And it's of particular interest because it's most closely related to the moment angle case, where you have a D2 and an S1. So I will include the suspension. He said, so there was a homotopy equivalence between the suspension of this polyhedral product and the suspension of a wedge, where you look at all of the index sets that are not in K, and you have a suspension of a geometric realization of a full subcomplex smashed with, and now Martin's notation I think was this, right, where A smash I is AI1 smashed down to AIK if I is the sequence I1 down through IK. Okay. And the key here is that this is happening after one suspension. Okay? And it's natural if you are doing homotopy theory to say, well, what I really want to know is not the homotopy type of the suspension of the space that I care about, but the space itself. So the question, what is the homotopy type of the polyhedral product itself? Okay. So a very naive guess might be that you can just remove the suspensions. Right? But this is wrong. And why is it wrong? Well, it's easy to find examples where this fails. So if you take K to be the boundary of a square, then it's fairly easy to see that in the case of the moment angle complex, this would be an S3 cross S3. Or in the case of a Conon AA, oh, it's a bit messier, so I won't write that down. You have an S3 cross S3, and this is not quite doing the right thing. So if you suspend this, then you're suspending a product, and Martin observed during his proof of the big theorem that this would break up as a suspension of S3, wedge another suspension of S3, wedge a suspension of the smash of S3 with itself. And if you just translate this naive guess, then the guess would say that ZK should be S3 wedge S3 wedge S6. And it's not, right? And what failed was that this space has a cup product in cohomology, whereas this one does not, right? So as soon as you have cup products, there's no chance of getting a desuspension of this theorem. So an obstruction to desuspending is some cup product information. So that says that you won't always desuspend, but maybe sometimes you do. Okay, so your next, is there an example where you do have a desuspension? Right, and we'll go back to Martin's nice example of 2 points. And we know that, say, ZK, for example, is then an S3. The decomposition here, in the case of ZK, would give that the suspension of our ZK in this point would be an S4, and ZK really does desuspend this time, okay? So this time it works. So sometimes you get a desuspension and sometimes you don't. So the question then becomes, for which K is there a desuspension? And probably there's a difference here already compared to anything we've heard in any of the earlier talks, either the geometric talks or the more topological talks, where you tended to have statements that worked kind of all the time. You know, pick a K and you just get results, right? Where here you're trying to distinguish between one set of simplicial complexes that has a certain set of properties and another set that has a different set of properties. Okay. So we need a way to analyze these polyhedral products to try to get to an answer, right? So we need to analyze K and these polyhedral products for conon AA with respect to K. And how are we going to do that? Okay, so these have been studied for quite a while, and there's a number of answers known that we will touch upon as we go along, but let's just forget that we know anything at this point and go back to step 0, okay? So the first step is to try and think about simplicial complex and see if we can say something about it that will let us get some insight into how they're built up. Okay, so we'll think about K. Will be on the vertex set M, so vertices 1 through M. And we're going to pick a vertex V. And we can think of some ingredient simplicial complexes. We can look at the restriction, K without V. So this you could think of, it's the full subcomplex on all of the vertices excluding V. Or you can think of it as all of the, well, just phrased differently, all of the faces in K such that V is not in that face. And you can think about the star. And this is all of the faces in K in which V is a vertex. And in the last talk, Martin defined a link. And in this case, with the link of a vertex, an easy way to think of it is the intersection of the restriction and the star. And when you organize things like this, you have two things and their intersection, and then K will be the union of these two guys over the link. So you get a push out of simplicial complexes where you have the link including into the star, and the link includes into the restriction. And together they give you K. So for example, let's look at something like that. Okay, there's my K. And let's pick V to be vertex 4, and then K without V, this is K. K without V is the full subcomplex on vertices 1, 2, and 3. The star is going to be all of the faces that have 4 in it. So all the faces with 4 in it, you get something that looks like this. You just exclude these two edges. And then the link would be the intersection of these two things. And the intersection is just going to be the 3 vertices, 1, 2, and 3 that are in common. And you can see that if you take these two guys, glue them together along these vertices, you recover the simplicial complex you started with. Okay.
Maybe you want to tell the people quite a little what restriction and star is talking about. Otherwise, you don't have intersection the way you wrote it. You might want to say these are maximal simplices in star and K.
All right. Well, you could say that this is the full subcomplex.
Yeah.
On all the vertices except V.
No, this is okay. The star is not.
Oh, the star is wrong.
You can just say that it's a generator.
These are maximal.
Oh, okay, okay.
We need to know who the star is.
All right, I'll just, yeah. All right. The example sort of gives you the picture. All right. Okay. We could keep playing with this a little bit. So I need another definition. So in general, the join of two simplicial complexes K and L is a new simplicial complex. You think of these as being on different vertex sets, and then you can take the union of all the faces in K or faces in L. Right? And in particular, in this case, the star will be the link joined with V. So if we go back to this example, if we start with the link and we've got an extra vertex in 4 down here, and you connect it to everything in the link, then you get the star. All right, so we can rewrite this star in terms of a link. And the advantage in doing all of this, the advantage in writing the simplicial complex as a push-out like this, is that you hopefully kind of set yourself up to do some inductive thing, because the restriction has fewer vertices than K. The link is a subcomplex of it, so it has fewer vertices. The star might have the same number of vertices as K, as in this example, but because you can write it in terms of the link, it's really based around a simplicial complex that's got fewer vertices. So you kind of set yourself up to hopefully do an induction at some point. So there's an advantage to this push-out, is that it's well set up for inductions. Okay. Right, okay, so where are we? We're trying to think about desuspending the BBCG homotopy equivalence, and we're trying to get our hands on some kind of information. We have some information about the simplicial complexes. Now let's introduce some information about how this push out of simplicial complexes translates into some information about polyhedral products. And to do this, we need, let's see, think about taking polyhedral products of the various complexes that show up in this pushout. All right, so K is on M vertices, right? And from the definition of a polyhedral product, right, it was the union of all of these length M products, yi's, where some of them were cone-on A's and some of them were A's, okay? And now you're going to compare it to something like the restriction, but that's got a smaller number of vertices. So, and the star, well, in this case, this example, it had the same number, but potentially it's got a smaller number, and the link has a smaller number. So if you're trying to think about constructing a description of cone-on AAK in terms of those ingredient pieces, you're not going to be able to do it if you're restricting to the number of vertices in each of the ingredient bits. So you need to think about having everybody having products of length M. Right? So it might have to introduce some ghost vertices. So so we need to think of, say, K without V and the other guys as simplicial complexes on this vertex set M. So we might have to introduce some ghost vertices, right? With the restriction, for example, it's missing vertex V, but we still have to think of V as kind of secretly being there in the background. All right, so to do this, so we'll write something like K without V bar for K without V on the vertex set M. Right, just keeping in mind that it's the same simplicial complex, but on a slightly different vertex set. Now, if we do that, there's a theorem due to Yellen and myself, which says that this push out of simplicial complexes translates into a push out of topological spaces involving these simplicial complexes with ghost vertices. And it always works even for XA. So I'll just, well, okay. Yes? Oh, I'm sorry. Yes, thank you. Thank you. Yeah.
Bar construction.
Yes, it's the bar construction. You wait till I get to the co-bar construction. Okay. This looks ugly, so let's try and figure out what this is really saying, right? Think about this, for example, okay? So if we look at cone on A, K bar V. Okay, so again, the ingredient bits are things like some product of yi's from 1 to m, where each of the yi's is the big space, if I is in a simplex, and it's the little space if I is not in the simplex. Think about V as being the mth term here, just so it's easier, right? You've got this list of m products, and with the bar notation, it means that V is not there. It's a ghost vertex. So it's thinking about it occurring at the end. You've always got this ghost vertex, and the ghost vertex is not in sigma. So this is going to look like a product of yi's through the first m minus 1 terms, which goes with k without v, and then you'll have an a in the last term. And that's going to happen no matter what simplex you put in, because none of the simplices in k without v has that last term in it, right? So this is going to look exactly like conon AA for k without v, and you've taken all of that and crossed it with the A corresponding to vertex V. And the link will be the same thing. Now, okay. Now I'm slightly cheating here because the link, strictly speaking, could have fewer vertices, and that means there's actually some ghost vertices in here, but then the notation goes berserk, right? Gabby? No, you're right. This works for any XA, but I can't write down too many pushouts, but you're absolutely right. Yeah. Yes. Right, okay, and the other thing, if you think about the star, that's a slightly different case. The star was this join.
The AB is not in the correct place, unless it's really the last verse.
Okay, well, I've got a shift, there has to be, yeah. All right, permute the vertices if you want. So the star is a join, which is a slightly different case, and there's a general fact that says if you've got any polyhedral product, and you look at the polyhedral product for K join L, that's the same as the polyhedral product for K times the polyhedral product for L. All right, so in our case, we've got conon AA for the star. This is a join of the link. And so I'll write it in the first draft here, like that. And this is, you just have a single vertex, and that vertex is in that one vertex simplicial complex. So it would correspond to having a conon A here. So this is all right, so where are we? So we've got this push out and we've identified some of the ingredient bits. So we can rewrite this push out. I'm going to leave a gap here where the link part I can write as the link cross AV, and the restriction part I'll write also with an AV. Both of these were missing the same vertex, and the same argument that shows that you can pull out a copy of AV as a product says that the map here will respect that product. So I'll just write that down. So this is some F cross an identity. Yes?
That was one you were on the right side of the board. No, you forgot the bar on this part.
Yeah, you don't have the bar and the bar.
Oh, here.
Oh, no. Left side, star key on two.
Ah, okay. Yeah, so
So that changes the CA at B. We've got, yeah.
all right. Yes, you're right. So there should have been a bar here, but I'm thinking of the link as being on the vertex set 1 through all of the vertices except V, right? And then here's vertex B. Yeah, okay, thanks. Right, and then over here, okay, so we've got for the star part, we had a link and a cone on AV. And finally down here, we've got this guy. All right, so we've got some push out for we've translated this push out into something that's slightly more recognizable. Cone on AV is contractible, so let's just rub that out and think of this as being a projection. And then you don't have a push out on the nose, but you do have one up to homotopy. And we're thinking about homotopy types of these polyhedral products, so that's good enough. Okay. So where are we again? We're trying to find out something about homotopy types of polyhedral products of the form cone on AAK. We did this little bit of analysis of the simplicial complex, translated it into some sort of analysis of a pushout that defines this, right? And then you can say, well, is this enough information to identify this polyhedral product? Not quite, but there is something you can say. There's an awful lot of noise here. So let's just abstract this a little bit. So now we're doing the next step. Let's bring in some homotopy theory. We'd like to use this pushout to help identify the homotopy type of cone on AA for K. So if we abstract a little bit, we look at a homotopy pushout, what we've really got here is something that looks like an A cross B projecting to A, mapping down to a C cross B by some map across an identity, and then you take a homotopy pushout. All right, can you say something about the homotopy type of Q? And it turns out you can. So let's let G be the inclusion of C into C cross B, and then map it to Q. And let's let D be the cofiber, or homotopy cofiber, of G. Then there is a homotopy cofibration where if we do this map G, you can identify its cofiber as D smash B, and there's a section. You can't necessarily add these two maps because Q might not be a co-H space. But in our case, this says something interesting.
There's something wrong there. Call D the cofiber of G.
And then you're saying the cofiber is D smash B.
Oh, yeah, you're right. What did I? No, I didn't. Oh, sorry. D is the cofiber of F. Thank you. Right, so in our case, we get this homotopy cofibration where the C is conon AA for the restriction. Where are we? Here it is. And then we'll go into conon AA for K. And the cofiber is this D, which is the cofiber of the link into the restriction. Smash with the B in this case is AV. All right. And there's a section here. In particular, after you suspend, this will break up as a wedge of this and this. At this point, there's sort of two things to say. One is there's been no restriction on K to this point, okay? So it's too much. We saw these examples of conon AAs where you couldn't desuspend the BBCG equivalence. So it's too much to hope that this sort of information is going to give you an answer for every K. On the other hand, I'll save my second comment for a bit. So you can look at a special case here. When the map F is trivial, right? And then if the map F is trivial, then its cofiber is going to be C wedge suspension A. So you'll get a bit more information about this left side, this right side. And there's actually some more information, and now you will get a splitting. Abstractly, it's just some random map. In this case, it's the map from the link into the restriction. Yep. So in the special case, when f is trivial, you end up with the cofibration splitting, and you get reorganizing the terms a little bit. You get it in terms of the restriction, half smashed with AV, and I'll say what that is in a moment, wedged with the suspension of, I lost where I am, the link, polyhedral product for the link, smashed with AV. Here, this half smash is, in general, an x half smash y is x cross y, and you're going to quotient out the y. Just collapse the y to a point. Okay. We'll use this because it's identifying a homotopy type in an interesting way. My comment that I left out for this general case was there's something going on here. This, as far as I know, has never been, I've never seen it published or used or anything like that. I think it's good for something. I don't know what. So as an open question, is there a way to use this to say something about polyhedral products in general? Could you use this, for example, to sort of give a different formulation of a BBCG equivalence after you suspend once things do break up? I don't know. There's something interesting there. But we want not suspensions, we want polyhedral products on the nose. Well, you used it, yes, to, no, so it was to get rid of the extra term here. This was a cone on A. So contracting that gave you a projection, and the fact that this is a projection plays into this homotopy type. Right, okay. Well, something interesting happened here in this special case, because now we've got the polyhedral product for K written in terms of polyhedral products that have fewer vertices, and we're pulling out copies of A's. That smells like an induction, okay? So the step 4 is let's think of a hypothesis. Right, so let's let script F be the family of simplicial complexes where you say that a simplicial complex is in this family if two things happen. The first is there is some vertex V in K such that you had this condition that the map from the link to the restriction is null homotopic. And the second is the inductive part, which is when you look at the link, or when you look at the restriction and the link, these are in the same family, right? So that means that each of them has a vertex which has a corresponding link into a restriction being null, which lets you do this again for this term and this term. And then you can iteratively do this to pull out copies of A's.
The link part of your decomposition is already suspended.
Oh, yeah, right. So yeah. So you could apply BBCG here,
Yeah.
right? But let's not, and let's
Okay.
just keep going. But you're right, yeah. So you could iterate on both of these parts to keep pulling out copies of A's, right? And do it one vertex at a time until you're left with something with, you would say, one vertex, although then you've got a contractible space and you don't quite recognize that you have a suspension here. So if you think about it as having two vertices, then you've either pulled out two vertices, there's only two choices. You've either got two vertices or an edge. And the edge part would have a polyhedral product that looks like a cone on A vertex 1 times cone on A vertex 2, and that's contractible. Or just the two vertices, and that would have a polyhedral product that looks like an A for vertex 1, smashed with an A for vertex 2, and a suspension thrown in. So you're always getting a suspension. So if you're in this family, this thing breaks down as a wedge of suspensions of iterated smashes of A's. So I'll get to your question in a moment, Martin. Yes.
How strongly does that property depend on A? In other words, if K satisfies it for some A, is it going to satisfy for all A's, or is just that ridiculous?
Well, that's sort of an interesting question. I was assuming it satisfied it for all A's, but you could potentially have, I mean,
So what you mean
there's
there by that family is for all A at this point, but not a specific A for, it seems like the A is sort of like a label that's being carried along in some sense, and it doesn't depend on it, it's just a curiosity.
That's the way I'm thinking about it. It's not really depending on the A,
Okay.
but
Property is simply a common.
Right, but it's not obvious. Lower that. Would anyone else like to?
So do we have a combinatorial description in terms of simple complexes? If all the A's are the same, I mean, or if we have S1 and D2. for example.
you've anticipated my next
Okay.
comment, yeah. Right, okay, so step 5 here is remember that the BBCG equivalence says that when you suspend this polyhedral product, you get something that looks like a suspension of gadgets that look like this. Right? And we're trying to compare it to something like this, right? So to address the question, if you're careful about how you do the bookkeeping, it's a non-trivial exercise, but if you bookkeep, you'll see that you're getting the same bits coming out, right? There's smashes of A's, the geometric realizations of the KIs are circles or they're spheres, so they're just extra suspensions. So bookkeeping and I don't want to go into bookkeeping, but you've got a desuspension. All right. Where are we in this big program? We're trying to find homotopy types that of polyhedral products of the form conon AA that desuspend the BBCG equivalence. We've gone through this analysis of simplicial complexes, turned it into push-outs of polyhedral products, analyzed them, threw in a hypothesis, and found out we get a decomposition. We get a desuspension. Then the next question is, well, maybe there are no simplicial complexes that satisfy this. Maybe this family is empty, and then we've done nothing, okay? So step 6. Yeah. Step 6 is, does this say anything for real? So we need find families of simplicial complexes that satisfy the hypothesis.
Look on Google.
Okay. And happily there are some. Okay. So they exist. There are, for example, I'm not going to give definitions of these various families. I'm just going to name them. Right? The first batch that came around are called shifted complexes, and it was an argument of Jelena and myself, and simultaneously by Theriault and Kishimoto. That you had this BBCG desuspension rather, for shifted complexes. And then it expanded out to something like, you would have sort of the Alexander duals of shellable complexes. And that was Theriault and Kishimoto again. And there was some other families. So I'll put some dots here for the moment. There's some other, either other families, and you can think of maybe other approaches. I mean, we went through some particular approach, right, where we looked at this Starlink restriction push out and then analyzed it on the level of polyhedral products and made a hypothesis and sort of played some games. Maybe there's a different approach. Sorry, this question?
Is one a subset of the other?
Yes, thanks. All these shifted guys satisfy that property. So some other examples or approaches where you might have some success. If you glue two centrifugal complexes along a common face, so say K and L, and then if BBCG desuspends for the Conon AA polyhedral products for K and L, if these desuspend BBCG, so does the glued guy. You could iterate this. You could iterate that and get something like something or another. If you iterate, you could do something for the one skeleton of a chordal graph. Or when K is flag. One skeleton is a chordal graph. There's been things done for some, I'll say, highly neighborly complexes. And a sort of a different organizing principle apart from this hypothesis. So yes?
Are you saying that the conditions hold for these families, or are you saying there's an unstable splitting? I mean, you've given two conditions. You've given two conditions which must be met, and then you get an unstable splitting, right?
Right.
But it's possible for unstable splittings to exist, and these conditions don't hold.
That's correct.
And
yeah.
So when you're listing these families, are these families for which an unstable splitting exists, or are they families for which the hypotheses hold?
Oh, sorry. These are families for which you get a desuspension of the BBCG theorem, regardless of whether or not they. Yeah. All right. So I'll just say the rest out loud. Irie and Kishimoto had what they called a fat wedge filtration argument that gave a sort of more, you can think of its aim as trying to identify as many of these simplicial complexes that satisfy the hypothesis as possible. And they got a very big family of them. And in terms of different approaches, apparently reading the abstract for Steve Amelot's talk, he has a different approach, which might render all of this obsolete and put us all out of business. But we'll have to wait for that until Tuesday.
Like 10 years.
Yeah.
Who's a great guy? Who did you say?
Steve Amelot.
Oh, Stephen.
Yeah, so with that, I'll close.
Well, that was a